This is MAT221, Calculus 1. This is Mrs. Johnson. We're in section 3.4 talking about the chain rule. And we just came up with this little hidden or mini chain rule for e to a number times x. So let's look at a couple more examples. Excuse me, I'm doing the Leibniz way again here in this example. I look at this and say, okay, the inside function would be 7 plus 5e to the 0.04x. Noticing again right here that I have that mini chain rule right here. But then I'm going to take this and say, okay, how could I rewrite this outside function? It could be written as t to the 1/2 power. Taking the derivative of this piece would be 7 was 0, then plus 5e to the, again, this is a number times x, so this is our little mini chain rule here, becomes 5 times 0.04 e to the 0.04x, and 5 times 0.04 is 0.2, and the derivative of this piece is equal to 1/2 t to the -1/2. Multiplying them together, we get this, but we cannot leave t in our expression. We have to, again, replace it with our x value here. So here's our derivative, 1/2, 7 times 5e to the 0.04x to the -1/2 times 0.2 e to the 0.04x. Now I could clean this up a little bit and multiply the 1/2 and the 0.2 to get a 0.1, but for right now, let's just leave the derivative as is. All right, let's do another example here. Again, this is an exponential function, but I don't have just an x as my exponent. I have something else here. So that becomes my inside function. My outside function can be written as 275 times 1.04 to the t. Taking the derivative of the t piece, I get 2x. Taking the derivative of this piece, this is the constant multiple rule and the exponential rule, which is 275 times 1.04 to the t times the natural log of its base. Multiplying those two pieces together, we get this. And then lastly, we have to substitute that value back in to get our answer in terms of all x's. So substituting the x squared in for t. All right, I'm going to start doing some examples now, doing the chain rule using Newton's way of doing the chain rule. Now remember, Newton did not take the two pieces apart. He just said, look at the derivative of the outside function, take its derivative, leaving the inside function alone, and then times the derivative of the inside function. So I'm going to show you this piece. I'm going to say, okay, if this is my function, this is 9 minus 4x to the 1/2 power. So the 1/2 power, or the radical, is the outside function. So I'm going to take that derivative first. Taking the derivative of the outside, the 1/2 would come to the front, and I would subtract 1 from the exponent, leaving the inside function untouched. And then Newton said, multiply by the derivative of that inside function. The derivative of that inside function is -4. And then I cleaned it up a bit to get this as my answer. This is my derivative of that expression. All right, let's see if you can do another one, doing it using Leibniz, not using Leibniz notation, using Newton's notation. If you can't, you can still go back and do Leibniz notation the way where he did t's and u's, or u's and y's, whatever you want to use. I'm going to use Newton. Newton says outside function, which is the 12 and the 3/2. I'm going to multiply those two together and subtract 1 from the exponent. So 18, leaving the inside function alone, to the 1/2, times the derivative of the inside function. And then I just multiplied all those numbers together. This is the derivative of that expression. Now for this one, I could use the quotient rule here, and the quotient rule says the derivative of the denominator, leave it alone, times the derivative of the numerator, which is 0, minus the numerator, -5, times the derivative of the denominator. Now I'm using the chain rule here because it's a function inside a function. It's a cubic inside a quartic. Excuse me, it's a cubic inside a quadratic. I'm going to bring the 2 to the front, leave the inside function, subtract 1 from the exponent. So 2 came to the front, leave the inside function alone, 1 to the exponent. Then multiply by the derivative of the inside function. And then all over the denominator squared. Now in this case, I'm going to do a little bit of algebra here too. If we clean up the numerator, notice we get negative times a negative. This becomes 0 over here. And notice now this is a GCF of the numerator, so I actually can cancel one of those terms because it's a GCF of one of those values. So we get 5 times 2 times 6, which is 60x squared in the numerator, over 2x cubed plus 1 cubed. All right, sometimes it's not so obvious that we can see the chain rule here. But again, I'm going to use Newton's method, Newton's way, to find the derivative here. Again, the inside function is actually the exponent. It is a cubic inside an e function. The outside function is the exponential function of e. So how do we take the derivative of e? Well, e is going to be itself, but in this case, we're going to keep the inside function. So using my rules, I get e to the inside function left alone times the derivative of the inside function. So notice this part was the derivative of the outside function, keeping the inside function untouched. And then I multiplied by the derivative of the inside function. This is Newton's way of doing the chain rule. Now if you have done this with Leibniz method, you would have gotten the same answer, just in a different order. So the most common mistake in this unit is to forget to use the chain rule. Don't forget to use the chain rule. Quite honestly, every derivative problem that we've been doing so far can actually be thought of as a chain rule problem. For instance, when we were doing the derivative of x squared, which we totally know now is going to equal 2x, technically, it's going to be the derivative of the outside function, which is that 2 drops to the front, subtract 1 from the exponent, times the derivative of the inside function, but the derivative of the inside function was just x, so the derivative of just x is 1. But we never did that step because it was silly to do that step, because the derivative of the inside function of x is always going to be 1, right? So our derivative was 2x. But we actually, when we get to unit 4, we're going to use this as a useful tool to take the derivative with respect to any variable we want, not just x. So that finishes up our PowerPoint. Let me see if I can get where I wanted to be at the very end of here. So this was all of our examples that we just went through. So please work on WebAssign for section 3.4 on the chain rule. There are also several worksheets in the worksheet folder that you should be working on to look at. The answers are also in the worksheet folder. That will really help you really practice this chain rule and practice how we take the derivative using the chain rule. Good luck. Have a good day.